Students, what we did in the last class, we will just have a recap of what we did in the last class. We saw why initial conditions are required. We saw that it helps us in obtaining the arbitrary constants of the differential equations, and we saw that how the circuit behaves. With the knowledge of the initial conditions, we can anticipate the form of response, and we can see how the element individually behaves, and in a combined network how the circuit is going to behave. And we saw the geometrical interpretation of the initial conditions. In the last class, we even saw what we mean by the derivative of current at t equal to 0 plus the second derivative of current. We saw how the current is going to vary, what was the slope, what is the initial point, and how the slope changes with respect to time. And we saw what is the procedure we follow to obtain the initial conditions. And in this class, just a recap, the resistance behaves like R at t equal to 0 plus, and the inductor acts as an open circuit by the virtue of its property. It does not allow any sudden change in current. So, it acts as an open circuit at t equal to infinity, it acts as a short circuit. Similarly, the capacitor without any initial charge in the circuit, there will be no voltage across the capacitor. It acts as a short circuit at t equal to 0 plus. This table is very important. Please keep it handy so that it helps you in analyzing the circuit as we go ahead. And the capacitor final state at t equal to infinity means the steady state, it acts as a open circuit. Similarly, I have got two more conditions where there will be a current flowing through the inductor before the switch changes. With an initial current through the inductor, it behaves like a current source because it does not allow any sudden change in current, and it acts as a short circuit finally. This just indicates that it acted as a current source and then finally it is acting as a short. A capacitor with initial charge of Q naught will act as a voltage source at t equal to 0 plus, and then finally it behaves like a open circuit. So, overall if you just see, R behaves as R and R, there is no change. Inductor acts as an open circuit finally and acts as a short circuit. Capacitor acts as a short and then a open circuit. With initial current, it acts as a current source. With initial charge, it acts as a voltage source at t equal to 0 plus. With this knowledge, what we saw in the last class, we will just see the procedure to be followed given any network for that matter. We will just start off with the basic networks today, simple RL, RC, and later on we will transit to RLC networks. Given a network, we need to follow the procedure. This procedure, history of the network at t equal to 0 plus. History becomes very important to analyze whether there was a current flow through the inductor or there was a charge across the capacitor before the switch is being closed or opened. It can be a closing switch, it can be opening switch. So, the history of the network at t equal to 0 plus, at t equal to 0 minus history means before the switch is being closed or opened. We need to know what is the current and what is the voltage across the capacitor. If there is an inductor, kindly find the current through the inductor and keep it aside. After the switching action takes place at t equal to 0. Write the network at t equal to 0 plus. 0 plus, just now we saw how the inductors and capacitors are going to behave. Inductor is going to act as a open circuit because it does not allow any sudden change if there is no current. With that, write the network at t equal to 0 plus, which helps us in evaluating the current at 0 plus and the voltage at 0 plus. Preferably current through the inductor and voltage across the capacitor. Write the general network after switching. I will just keep revisiting to this slide every now and then. General network after switching, write the integral differential equations for the general network. Obtain an expression for the first derivative, do manipulation so that you get the first derivative di by dt, and evaluate di by dt at 0 plus by knowing the values of I at 0 plus, which was calculated here, and the voltage if required. Afterwards, differentiate the equation which was written for the general network again to get the expression for the second derivative, and using the initial conditions of I at 0 plus, di by dt at 0 plus, evaluate the second derivative, these terms can be even for voltage dV by dt, dV by dt at 0 plus or d squared V by dt squared at 0 plus. So, with the knowledge of this, we will go to the problem. I have taken few simple problems for today. Later on in the next class, we will take up problems on RLC with 2 loop networks and so on. First, let us try to understand. With this knowledge, I think we can go ahead with 2 loop network and analyze this. So, this is the problems on initial conditions. We will see how this knowledge will help us in understanding the solution of differential equation or to evaluate the arbitrary constants of the differential equation. The first problem is, if the switch K is closed at t equal to 0, please see it is highlighted as closed, and I have another circuit where the switch is opened at t equal to 0. We will come back to this after some time. We will just take a problem where the switch is closed at t equal to 0, means at t equal to 0 minus the switch is open. I will just copy this circuit on the board and we will go ahead with finding the solution of this particular circuit, RL circuit. The circuit is a very simple circuit where there is a switch, there is a resistor and there is an inductor. R, L and V, where the switch is being closed at t equal to 0. When we are writing Kirchhoff's voltage law to the loop, we need to know what is the voltage across the resistor, what is the voltage across the inductor, what is the voltage across the capacitor. So, it is gone by simple voltage across the resistor is given by I into R, voltage across the inductor is given by L di by dt, voltage across the capacitor is given by 1 by C integral I dt. We will keep this in one place. I told you the first thing what we are supposed to do given a problem is, he says the voltage is 100 volts, the value of the resistor given is 10 ohms, 10 ohm resistor, and the value of the inductor is 1 Henry. So, how do you find? Normally they will ask you to find the current at 0 plus, di by dt at 0 plus and d squared I by dt squared at 0 plus. So, we have seen how to go about in the previous slide the history of the network. First thing is the history of the network is, I need to know what is the history of the network at t equal to 0 minus, means at t equal to 0 minus, switch was open. I will just take this problem bit slowly and carefully, try to understand. Switch is open, what will be the current through the inductor at 0 minus? It will be 0. So, with this switching happens, if you just see the second, switching takes place at t equal to 0. The switch is closed at t equal to 0. This is the history of the network. 0 minus is 0. The switch is closed at t equal to 0. Immediately after the switch is closed, it says write the network at t equal to 0 plus. Network at t equal to 0 plus. There is a voltage source, switch is closed, resistor behaves as R, we have seen that. Inductor acts as, because there is no current, it does not allow any sudden change in current, it acts as an open circuit. So, if you want to evaluate the current at t equal to 0 plus, this network will help us in understanding I at 0 plus is 0. You can just observe the inductor will not allow any sudden change in current. This is a case where there was no current before, even after the switch was closed, there is no current afterwards. What is the third step? We have evaluated I at 0 plus, we have evaluated I at 0 plus. Write the general network after switching. We will see general network after switching means the next step, switch is closed, write R, and L as it is, V, R and L. I will write a Kirchhoff's voltage law, KVL, for the loop. It will be V is equal to R into I plus L di by dt. This is what given, right? Integro differential equations. See the next line. These steps are very important. If you just follow this, you can arrive at the answers, right answers. Write integro differential equations of the given network. Integro differential equation is the DC source, V is equal to R into I plus L di by dt. This is the voltage across the resistor, this is the voltage across the inductor, and this is your supply voltage. Get an expression for di by dt. Manipulate this equation. See that the coefficient of the derivative is equal to 1. Rearrange this equation to get di by dt equal to V minus R into I divided by L. I have seen that the coefficient of the derivative is 1. So, I brought this L below, it is V by L minus R into I by L. Now, I need to evaluate the derivative of the current at t equal to 0 plus. Substitute the values obtained, obtain an expression, we have done with this. Now, we see using initial values like I at 0 plus, we can find out di by dt at 0 plus. I have an expression for di by dt. Substitute the values to find all these. When I say I, it is all with respect to time. Normally it is understood. Now, if I want put t equal to 0, di by dt at t equal to 0 plus equal to V by L minus R I at 0 plus by L. Just substitute the values given. I at 0 plus is 0. Therefore, this term goes to 0. It will be V by L. It is nothing but the voltage 100 divided by 1. So, the value of di by dt at 0 plus is 100. Please do not forget to write the units. It is amperes per second. Amperes per second is the unit for di by dt. Now, what we need to do, I have already obtained the value of di by dt. We got I at 0 plus as 0. Di by dt is 100 amperes per second, which is a positive value. And let us see how to obtain the second derivative. Differentiating A, we get the second derivative. If you differentiate equation A, differentiating A, we get 0. Derivative of a constant, because this is a DC source, it is 0. R di by dt plus L d squared I by dt squared. It is equal to R into di by dt plus L d squared I by dt squared. That is what being said here. Obtain an expression for the second derivative. Obtain an expression for the second derivative. Using initial conditions, we know the values of I at 0 plus, di by dt at 0 plus, find d squared I by dt squared. So, we will come to the end of this problem. So, get an expression for d squared I by dt squared equal to minus R by L di by dt. This is at 0 plus, substitute the known values. I know di by dt at 0 plus is 100 amperes per second. I know the value of R and L, just substitute, you will get the value for d squared I by dt squared. D squared I by dt squared at 0 plus will be minus R is 10 divided by L is 1, di by dt is 100. So, I get this as minus 1000 amperes per second squared. So, we have obtained I at 0 plus di by dt at 0 plus d squared I by dt squared for a simple RL circuit. So, we have obtained for a simple RL circuit, we have got The answer as 0, 100 amperes per second and minus 1000 amperes per second squared. We will see in what way it is going to help us. Now, what information this gives us? Last time we discussed about the geometrical interpretation of the derivatives, the initial value, derivative and the second derivative. So, what it means is, if I just try to plot the current with respect to time, this gives me an information that it starts at 0, the current before the switch is closed, the current is 0, it starts at 0, it has a positive slope. For every problem we will try to understand what it means. This indicates a positive slope and it says that the rate of change of slope is negative, means it is going to gradually increase and finally settle down at a value. The final steady state value will be equal to, if you just substitute the final state, it is V by R because L acts as a short. At t equal to infinity, it is the voltage source, a switch, or L behaves as a short circuit. This is what we saw in the slides. We saw that it acts as a short circuit at t equal to infinity, inductor acts as a short circuit. So, the final current I at infinity is equal to V by R. So, it will be 100 by 10, it will be 10 amperes. So, your final steady state will be V by R. So, this is how the initial slope is positive, the rate of change of slope is negative. So, this is what I told you, it helps us in anticipating the form of the response. It helps us in understanding how the current is going to vary in case of a simple RL circuit in series. So, we will go to the next problem. A same RL circuit, but in this case there is a slight change. It is not a dual circuit, but we have a switch which is opening. There we wrote KVL equations, here we will be writing KCL equations. Here just see the problem, second problem we have that if switch K is open, at t equal to 0, here K was closed. Here we are seeing for this problem we say that the switch K is open and he has asked us to find not the currents, he has asked to find voltage dV by dt and d squared V by dt squared. So, on the same lines we will just go to the history and then we will see how to evaluate the requirement V. Instead of I, it is V dV by dt, d squared V by dt squared. So, this gives you overall picture. Instead of having the voltage across the resistor, voltage across the inductor, voltage across the capacitor, I need to know what is the current through the resistor, current through the inductor, current through the capacitor. What is the current through the resistor? It is P by R. Current through the inductor 1 by L integral V dt. Current through the capacitor is C dV by dt. So, with this expression for currents, we will be writing the Kirchhoff's current law for the second circuit. So, I will rub this, we will go to the second problem. For the second problem what you have taken, it is nothing but a current source. I have a switch which is the opening switch, I have a resistor, I have an inductor. The value of the current source is 1 ampere, the value of the resistor is 100 ohms. Value of the inductor happens to be 1 Henry. He has asked us to find V, that is nothing but the node voltage, V, this is your reference, V at 0 plus, dV by dt at 0 plus, d squared V by dt squared at 0 plus. Then we can understand how the voltage across this circuit varies when a current source is applied. Initially at t equal to 0 minus, first thing is history of the network. At t equal to 0 minus, switch was closed, switch closed. This is very important. History becomes very important, so that if we go wrong in history, the future will be wrong, because we need to understand these elements in a better way. At t equal to 0 minus, the switch is closed. Once I say the switch is closed, there will be no current through the inductor. At 0 minus, the current through the inductor is 0. Before the switch is closed, the current is 0. There is no current through the resistor also. The current will be circulating through this, because the short circuit, the current finds the least resistance path. It will never go through the inductor or resistor. So, this case the circuit will be, I have a current source with a closed switch and a resistor and an inductor becomes redundant. So, the current will be through this, the voltage across this will be 0. So, with this, at t equal to 0, switch is opened, We need to understand what happens to the circuit after the switch is opened. Once the switch is opened at t equal to 0 plus, just let us go back to what we saw in the, we have to look at the history of the network. We saw this. Switching action takes place at t equal to 0, that is why we have written switching action. It can be opening or a closing switch. In this case, it is opening switch. We need to write the network at t equal to 0 plus. If I have to write the network at t equal to 0 plus, network at t equal to 0 plus, I have a current source, switch is open, there is no point in showing that. I have a resistor, behaves as R, inductor acts as an open circuit, because there was no current before, it will not allow any current immediately after the switch is closed. It allows a gradual change in current. Therefore, this is I, this is R, this is your voltage with respect to the reference. The voltage V at 0 plus, will be I into R. So, it will be current of 1 amperes into 100 ohm resistance, it will be 100 volts is V at 0 plus. We have obtained the value of voltage at 0 plus as 100 volts. Similarly, write the integral differential equation, write the general network after switching. It is nothing but a current source, a resistance and a inductor R, L and I with V. Write the general integral differential equations. If it is I, general integral differential equation is I, current through the resistance is V by R plus current through the inductor is 1 by L integral V dt. So, what was the current through the inductor? This was current through the inductor, this is current through the resistance. What we want is dV by dt. I do not have a term of derivative here. I will differentiate this equation. I call this as equation B. I differentiate equation B. If I differentiate this equation, this is a constant current source, it will be 0. Differentiating, I get 1 by R dV by dt plus V by L. If I rearrange, I will get an expression for dV by dt. That is what I said. Write integral differential equations of the network. After switching, we found the voltage at 0 plus. Now obtain an expression for the first derivative. Instead of di, we got dV by dt. We got an expression for dV by dt in this case. So dV by dt, rearrange these terms, it is minus V R by L. If you want to evaluate the derivative of voltage at t equal to 0 plus, substitute for t, this will be at 0 plus, this will be voltage at 0 plus, just substitute the values, you will get dV by dt at 0 plus will be minus V at 0 plus, we know it is 100, it was 100 volts, R is 100 divided by L is 1. So, the value of this will be minus volts per second. So, this will be the expression for V. What about the second derivative? Differentiate this equation again. It has already been differentiated once. Differentiate this equation, obtain an expression for the second derivative. Once the second derivative, you get an expression, substitute the values of V at 0 plus, dV by dt at 0 plus, and then obtain an expression for the value for d squared V by dt squared by substituting the values. The second derivative is, if you differentiate this equation again, you will get 0 equal to 1 by R d squared V by dt squared plus 1 by L dV by dt. Therefore, d squared V by dt squared will be minus R by L dV by dt. If you want the expression at 0 plus, substitute at t equal to 0, you will get d squared V by dt squared at 0 plus will be minus 100 by 1, dV by dt is minus 10,000. So, it will be plus 1 in 10 to the power of 6 volts per second squared. So, this will be the value of d squared V by dt squared. So, it is 10 to the power of 6 volts per second squared. This is plus, this is plus. This just tells us how the voltage is going to vary across an RL circuit. If I just plot, the y axis happens to be voltage because I am looking at voltage with respect to time. Once the switch is opened at t equal to 0, the starting point is 100 volts, the voltage across this will be 100 once the switch is opened. Switch is opened, the current flows through this axis is an open circuit we saw, and the voltage will be 100. We have a negative slope. Finally, if you just see what happens at the final state at t equal to infinity, at t equal to infinity, I have a current source, switch is open, I have a resistor, the inductor acts as a short circuit. All the current flows through this, the voltage at infinity will be 0, voltage at this point with respect to reference. The current will flow through this, it becomes redundant. So, this is quite interesting to understand. You need to know what happens to the current, the voltage at infinity. Because of the inductor, the current flows through this, the voltage becomes 0. Voltage across the short is 0. The current will not flow through a resistor because it chooses the least resistance path. So, if you just plot how the voltage is going to vary, it is positive, it starts at 100 volts, it has a negative slope, we discussed that in the previous class, it has a negative slope and the rate of change of slope is positive, gradually the negative slope becomes 0. Therefore, we know the final state, the voltage varies like this, the slope is gradually changing. So, this is how the voltage across an RL circuit behaves. So, I think we have gone very slowly in these two problems. Same thing will be extended to an RC network in the next slide. We have a RL, we just took both this we saw RL circuit and one is a series RL, the other one is a parallel RL, where when the switch was open and when the switch is closed, we saw these two. We will go to the next problem, that is RC circuit. So, only change is, instead of a inductor I have a capacitor in both the cases. The procedure is very simple, it is absolutely same. You need to look at the history, write the network at t equal to 0 plus, write a general network, obtain an integral differential equation, obtain an expression for the first derivative, and using the previous values obtain your di by dt or dv by dt as per your requirement, and then go ahead, you will get a solution. So, we will take a next problem with RC. We will just take a problem on RC. It is a RC series RC circuit, where voltage source, switch is a closing switch. I have a R, I have a C. The question here is V, R and C. The values of voltage is 100 volts, 1000 ohms, 1 microfarad. 100 volts, 1000 ohms, 1 microfarad capacitance. So, we will just, he has asked you to find I, di by dt, d squared I by dt squared at 0 plus, at 0 plus, at 0 plus. What are these values? First thing what you are supposed to do is find the history of the network. Slightly I will go a bit faster here. At t equal to 0 minus history, very important, history is very important. Switch is open, open switch. When the switch is open, the current through the circuit is 0, voltage across the capacitor is 0. There is no voltage, there is no charge, it is a relaxed circuit, there is no charge across the capacitor. So, the voltage across the capacitor is 0. Just observe, whenever we have an inductor, we find the current through the inductor. If there is a capacitor, we try to find the voltage across the capacitor, which may help us in analyzing or evaluating the other terms. So, what we need to do next? Network at t equal to 0 plus. Please do not forget the previous things. History of the network is obtained. We saw this. Switching action takes place at t equal to 0. Write the network at t equal to 0 plus. How do you write the network at t equal to 0 plus? It is a voltage source, switch is closed, R behaves as R, capacitor acts as a short circuit. This is from the previous slides. We know how the capacitor behaves. Capacitor at t equal to 0 plus acts as a short circuit. So, this is R, this is V. What will be the current through this? I at 0 plus will be V by R. It is nothing but 100 divided by 1000. So, the current at 0 plus will be 0.1 amperes. So, current at 0 plus is 0.1 amps. Capacitor acts as a short at t equal to 0 plus. This is the only change. In the previous case, it was an inductor. Inductor acts as open. Only change is the capacitor acts as short, but finally the capacitor acts as open. So, write general integral differential equation after switching. So, general network V, R, switch is closed, and C. V, R and C. general equation V is equal to R into I plus 1 by C integral I dt. This is the voltage across the capacitor. We saw that this is the voltage across the capacitor. So, V is equal to R into I plus 1 by C integral I dt. Obtain an expression for di by dt, right. Means if I want to obtain expression for di by dt, I need to differentiate this equation. Differentiating A, we get 0 equal to R di by dt plus I by C. Simplify this, di by dt equal to minus I by R C. Obtain expression for di by dt. So, di by dt at 0 plus, substitute for t equal to 0 plus, t equal to 0 wherever you got a variable with time. So, ti by dt at 0 plus is equal to minus I at 0 plus by R C, which is nothing but minus the current at 0 plus was 0.1 amperes. We know the current at 0 plus. R and C was 1000 into 1 micro, 1 into 10 to the power of minus 6. So, it is 3 and minus 3, it will be plus 3, it will be minus 100 amps per second. So, this works out to be minus 100 amps per second. So, di by dt will be minus 100 amperes per second. Just simplification, just substitute the values, you will get di by dt at t equal to 0 plus. If you want the second derivative, differentiate this again, differentiate B, it is 0 equal to R d squared I by dt squared plus 1 by C di by dt. Obtain an expression for the second derivative, substitute the known values of I at 0 plus di by dt at 0 plus and obtain d squared I by dt squared. So, d squared I by dt squared equal to minus 1 by R C di by dt. If you want to evaluate this at t equal to 0 plus, use it at 0 plus, just substitute the values, d squared I by dt squared at 0 plus will be minus 1 by R is 1000, 1 into 10 to the power of minus 6 into di by dt is minus 100. So, it will be 3 plus 5, it is 10 to the power of 5 amps per second squared. So, the actual value of the second derivative is 10 to the power of 5 amperes per second squared. What does this indicate? At t equal to infinity, I have a voltage source, switch is being closed, I have R, capacitor access open. I at infinity, I have not asked. If you want, you can see I at infinity equal to 0, because the capacitor initially acted as a short circuit. Just look at that particular table what we saw at the beginning of the class, the capacitor acting as open at infinity, that is at steady state. The steady state behavior is like open, it would have charged and the voltage across the capacitor will be V, this is R, current will be 0. If you are looking at the current is going to vary. If you just see I with respect to time, because it is a RC circuit, it starts at 0.1, it has a negative slope and it goes on, the rate of change is positive. So, it goes on decreasing and finally, the current goes to 0. So, this is how your current will be. You can anticipate the form of response. I am just trying to tell you with the known values of the derivative and the rate of change of slope and the initial value of current, I can literally see how the circuit behaves, how the current is going to change with time. So, it starts at a value which is positive. This is what we saw in the graphical interpretation of the derivatives in the very first class. It starts at 0 plus, immediately after switching the current will be 0.1, before that the current will be 0 before t equal to 0 minus, the current was 0. Immediately, because capacitor acts as short, the current will be equal to 0.1 amps, and gradually the slope is negative, the slope keeps changing, and finally it goes to 0. We saw that the current at infinity equal to 0. So, this is what we can make out. These are the answers for this. So, in RC, we saw K was closed switch. A similar problem what we did in RL we will be doing here. It is a switch is opening, it is not a closed switch, it is opening switch. So, on the same lines, try to analyze, look at the history, obtain the value of voltage. You are looking at voltage dV by dt and d squared V by dt squared. On the same lines, write the Kirchhoff's current law equations. These are going to help you in understanding the KCL equations given, and then we will take another problem. Now, it is simple RC in parallel. The fourth problem for today, we have a current source, we have an R, we have a capacitor, and the switch is a opening switch. The direction of the switch t equal to 0 indicates the switch is an opening switch with RC. Given that I equal to 10 amperes, it is not 1 amperes, I is equal to 10, R equal to 1000 ohms, capacitor is 1 microfarad. So, they have asked you to find, as usual, V dV by dt d squared V by dt squared at t equal to 0 plus. So, this is the questions will be like this normally. So, whenever we need to know what is the voltage, voltage means it is with respect to this is the only principal node what we have with respect to this reference, all are parallel. So, before the switch is history of the network, at t equal to 0 minus, the switch was closed, switch closed, when the switch is closed, the current will be flowing through the switch, there will be no voltage across the capacitor, there is no charge being deposited across the capacitor, there will be no current through the resistor. So, we just see voltage at 0 minus is 0, the current through the capacitor is 0, it is act as a short because of the switch. At t equal to 0, switch is opened, there is a change in the position of the switch. Whether the switch changes, is there any change in the elements, there will be one transition, one steady state. So, once at t equal to 0, the switch is opened, at t equal to 0 plus, write the network. We just see, write the network at t equal to 0 plus. So, in this t equal to 0 plus, if you write the network, I have a current source, switch is open, there is no point in representing a switch, I have an R, capacitor acts as a short circuit, because there is no voltage across it, the capacitor acts as a short circuit to this I. Even though R is there, this the capacitor acts as a short circuit. So, what will be the voltage? V at 0 plus, V at 0 plus will be 0. So, the voltage at 0 plus will be 0, because all the current will be flowing through this capacitor, the least resistance path, the resistor becomes redundant. At this instant of time, just for a short duration of time, right, the capacitor acts as short. So, all the current will flow through the capacitor, and the voltage across the capacitor or the voltage across this particular or this node voltage will be equal to 0. after the network, write the general network. General network after switching it will be a current source R and C. So, it is I, R and C, switch is open, and this is your node voltage V. Write the general integral differential equations. It is I equal to current through the resistor is V by R plus current through the capacitor is C dV by dt, C dV by dt. Obtain an expression for dV by dt. It's simple, rearrange these equations. dV by dt is equal to I minus V by R by C. I just made the coefficient of differential equation equal to 1. dV by dt is equal to I by C minus V by RC. So, the value of the derivative at 0 plus is V at 0 plus. V at 0 plus was 0. So, this term goes to 0. Voltage across the node is 0. So, it is nothing but I by C. Current is 10. Capacitance is 1 microfarad. 1 into 10 to the power of minus 6. So, 10 to the power of 5 volts per second. Okay. So, this will be your dV by dt. dV by dt is, the most important thing is the voltage is 0, dV by dt has a positive value, and the second derivative, differentiate this equation A again. So, you will get 0 equal to 1 by R dV by dt plus C d squared V by dt squared. So, d squared V by dt squared, if you rearrange, you will get minus 1 by RC dV by dt. If you want to know the expression at dV by dt at 0 plus, just substitute this, we get minus 1 by R is 1000, 10 to the power of minus 6 into dV by dt. So, dV by dt happens to be positive. So, if you just see it is a negative value, what I get? I will be literally not bothered about the magnitude, right? Magnitude, right? If I just know what happens, I can just anticipate the response voltage. Final state of your capacitor is open. If you just see V at infinity, if you just know what happens to the voltage at infinity, right? It will be the current source, resistance, capacitor acts as open. So, this will be the voltage, it is I into R. The voltage will be 10 into 1000, 10,000 volts at infinity. So, it settles down at a value, the voltage across this will be equal to the voltage across your resistor. So, if I just see the voltage curve, it starts at 0, it has a positive slope and gradually rate of change is negative. So, the slope goes on changing and settles down at a value at infinity. So, this is how you can understand, you can anticipate the response. It is V dV by dt, d squared V by dt squared for a given circuit. So, what we have done today is we have taken RL, RC circuits and we have gone through the derivatives, second derivatives and so on. So, in the next class, anyway, we will in fact we will take up this in the next class. We will see what happens in a circuit where this is a problem where we have two switches. In all the problems what we took, we had only one switch. This is a case where the switch is already at position A and what happens when it moves to B. So, there is already a transition which has occurred. We will see what happens when a switch is moved to B in the next class, and we will go ahead with some more problems on initial conditions. Later on we will take up the transient analysis, because your transient analysis initial conditions are very much essential to understand how to evaluate the arbitrary constants. Thank you.